Hello, welcome to my PhD presentation. In this presentation, I'll present the key contributions of my research titled Advanced Grant-Free NOMA and Hybrid Beamforming Techniques for 5G and Beyond. 5G and beyond applications are categorized into three main groups. Massive Machine Type Communication, or MMTC, shown in green circle here, is for IoT networks such as smart cities and smart homes. Enhanced Mobile Broadband, or EMBB, shown in blue circle, powers high throughput applications such as augmented reality and virtual reality and online gaming. And ultra reliable low latency, or URLC, shown in pinkish orange circle here, enables mission critical applications such as telemedicine and vehicle to vehicle communications. Through industrial collaboration, my PhD research addresses key challenges in MMTC and EMBB to bring these technologies closer to real-world deployment. In MMTC, the current transmission schemes suffer from high packet loss and low energy efficiency. My first research direction was tackling these issues. In EMBB, the main technology is millimeter wave communication, which faces major challenges in practice due to hardware impairments and high mobility users. Addressing these challenges has been my second research direction. URLC also faces many practical challenges. However, it falls outside of the scope of my work. In the next few slides, I'll walk you through my contributions toward improving MMTC transmission scheme. The state-of-the-art transmission scheme for MMTC is grant-free non-orthogonal multiple access, or grant-free NOMA. Being grant-free allows users to transmit without the common handshaking steps in grant-based communications. Therefore, it's more energy efficient. Also, NOMA allows users to share resources. Therefore, it can support massive connectivity. However, these features come with three significant challenges. First, being grant-free leads to high packet collision rates, especially in dense networks. Second, NOMA inherently suffers from low SINR, or signal to interference plus noise ratio, which results in high packet loss rate. And lastly, the lack of control channels in grant-free NOMA limits the retransmission strategies to basic methods, which are very inefficient. To improve reliability and energy efficiency of MMTC, I propose a decentralized solution to enable advanced retransmission methods called incremental redundancy, or IR, hybrid automatic repeat request, or HARQ, and grant-free NOMA. IR HARQ provides the highest successful packet decoding rate among retransmission methods. On the left-hand side, we see how it works. A coded packet is split into 4 redundancy versions, and at each retransmission, a different redundancy version, or RV, is sent. The receiver then combines these RVs to improve the decoding probability with each retransmission. However, IR HARQ requires auxiliary control channels to carry its metadata, and in grant-free NOMA, we don't have that. So I propose a decentralized solution to embed the HARQ metadata into the transmitted and retransmitted packets. In grant-free NOMA, each packet accompanies a preamble, which is originally used for user detection. I propose to use this preamble for detecting the RV index, and the order received RVs should get combined as well. On the right-hand side of this slide, I'm showing two mappings I propose between preambles and RV indices and preambles with each other. This allows the receiver to know how to combine the packets once it detects the preamble ID. Additionally, I optimize the preamble group sizes with mean energy efficiency of the IR HARQ retransmission as the objective. I developed a dynamic programming algorithm to compute the expected value of energy efficiency by modeling the retransmission process as a tree of states. The tree shown here captures all possible retransmission states and their probabilities using a recursive function. Also, memoization greatly improves the efficiency of this computation, especially when the number of retransmissions is high. In this plot, I'm showing energy efficiency of our proposed Grant-Free NOMA IR HARQ and two of its simplified variants I proposed called Grant-Free Chase Combining or CC HARQ and Grant-Free Single Transmission or GFST, shown in blue color, and 4 conventional methods in red color. We observed that the proposed Grant-Free IR HARQ and GFST methods outperformed the benchmark schemes. Moreover, this result essentially indicates that the optimal method between Grant-Free IR HARQ and GFST depends on the network load. I conclude this part of the presentation by positioning this work in the body of research on Grant-Free NOMA. Since our publication in 2021, Grant-Free NOMA research has progressed quite significantly, particularly in active user detection techniques and semi-grant-free methods for backward compatibility. To date, our work remains the only one to address advanced retransmission schemes in Grant-Free NOMA, highlighting its unique contribution to the field. Now I'll present my contributions toward improving robustness of EMBB or Enhanced Mobile Broadband Systems in the presence of hardware impairments. As I mentioned in the introduction, the key enabler of EMBB is millimeter wave communication. In millimeter wave, due to severe path loss, communication is feasible only with highly directional transmissions, which is a method called beamforming. Beamforming concentrates transmitted energy in directions that get to the user either through direct paths or through reflections, as illustrated here. There are 2 steps involved in this approach. In step 1, the base station and users collaborate to perform channel measurement that is essentially the characterization of the air interface. And in step 2, the base station uses channel measurements for designing the beamforming patterns, the 2 polar plots that are shown here and here. Beamforming can be implemented in 3 ways: digital, analog, and hybrid. For mobile networks, hybrid beamforming is the dominant approach, which strikes the best balance between cost, energy efficiency, and performance. This image shows the structure of a hybrid beamforming system. It is made up of analog parts, which are the antenna arrays, the phase shifters, and the oscillators shown here, and also here on the right-hand side, and a digital precoding and a digital combining modules as well. The challenge with beamforming systems is the hardware impairments. In these 2 plots, so here and here, I'm showing the hardware impairments in hybrid beamforming system. So oscillator which exists here, multiple oscillators exist here and also here at the receiver side, suffers from something which is called phase noise. And this phase noise has an interesting property. Its standard deviation increases with time, which means the problem becomes bigger and bigger. The distortion becomes bigger and bigger. Also, we have something called the quantization error for the phase shifter. We have limited resolution at the phase shifter, so that causes quantization error. Because of these 2 non-ideal or impairments attributed to the hardware, the generated pattern is going to be different from the intended pattern. The blue polar plots, the pair of them, is the intended pattern, which optimally uses the existing paths to transmit data to the user. But what we actually get in reality is the red patterns, which we don't know, which we don't know what it exactly looks like, because it is being caused by these errors. And in the field, in the deployment scenario, we don't do measurements over the beam pattern, but instead this is something that the network has to tolerate and has to be robust against. This mismatch between the intended pattern and what we actually get causes gain loss, which gets worse with time because phase noise accumulates over time and standard deviation increases over time. And the phase noise-induced beamforming mismatch prevents cost-efficient implementation of millimeter wave communication. And in my research, I explored ways to solve this issue for the state-of-the-art beamforming methods. Conventionally, beamforming matrices are designed by iteratively solving a non-convex optimization task with channel capacity or SINR as its objective function and with a few constraints as well. The state-of-the-art optimization methods, however, use ResNet-based self-supervised learning to process channel state information coming from the left in this picture and generate beamforming matrices shown on the right without any iterations. In this method, the loss function is a generalized mutual information rate called achievable information rate or AIR, and feasibility constraints are embedded into the structure of the neural network through activation functions of the last layer. So the activation functions shown here. The idea is to have the neural network learn to optimize the beamforming in one call of the neural network in the inference phase. This way, the non-convex optimization task is completely transferred to the offline training phase. This double branch neural network architecture, together with AIR as its loss function, is a state-of-the-art hybrid beamforming optimization approach. We're going to refer to this double branch architecture later in the presentation as well. So let's give it a short name. Let's call it System A. Despite its benefits, ResNet-based DNN is still vulnerable to phase noise because it doesn't have any mechanism to combat the increasing beamforming mismatch. To solve this, I took the ResNet structure shown on the left-hand side and attached to it a predistortor shown in the blue box on the right to enable the neural network to use the time index information to generate tailored beamforming patterns for each time index. This predistortor is essentially a modified version of the famous squeeze and excitation attention mechanism proposed in reference 1 here. This attention module takes time index and recalibrates ResNet's outputs based on that. I named this module Adaptive Squeeze and Excitation ResNet, or ADA-SE ResNet. I extended System A to multi-user MIMO OFDM scenario, which is the scenario our industry partner actually cared about for practical networks, and used ADA-SE ResNet as its core building block. This neural network follows the same design pattern as System A, which is the state-of-the-art, with ResNet blocks replaced by ADA-SE ResNet blocks. Let's call it System B. Different from System A, this system is trained using phase noise affected achievable information rate as the loss function, where both beamforming mismatch and intercarrier interference caused by phase noise affected. This particular loss function provides the necessary gradient signal during backpropagation to teach the DNN how to alleviate phase noise effects. This figure illustrates how our proposed solution copes with the oscillator's phase noise over time. As shown in the legends, dark shades of gray indicate beamforming at earlier time indices, while lighter grays indicate later time indices, with the red one as the last beamforming pattern of the frame, so the last one. We can see that the DNN learned to gradually smoothen the pattern as time passes to reduce sensitivity to phase noise-induced mismatches. Initially, it leverages highly directional beams for maximum gain, but as phase noise accumulates over time, it transitions into wider beam lobes to still hit the target despite a slight misalignment. This is completely owed to the adaptive attention module that I incorporated with the legacy ResNet-only structure. This figure presents the average AAR of 4 users under the compounded distortion of phase noise, phase shifter quantization, and channel state information error. The benchmarks CTDH and HOSVD are the conventional optimization-based methods I considered, and the one denoted by ResNet serves as a proxy for the state-of-the-art ML-based approaches that are adapted to our system setup. Our proposed method, shown in the black color, consistently outperforms all benchmarks with a wider performance gap observed under stronger phase noise conditions. Next, I'll present the extension of this work to high mobility scenarios. High mobility users cause channel distribution shift as they move from one environment to another. Distribution shift is actually a very common problem in machine learning, as it cannot be guaranteed that the training data set is a representative of every deployment scenario. In cellular communications, 3GPP, which is the standardization organization for cellular communications, classifies deployment channel distributions into 5 types, called cluster delay line, or CDL, types A, B, C, D, E. In reference to, it has been shown that a user trained on one CDL type experiences considerable degradation while traversing other ones. To address the channel distribution shift, state-of-the-art methods use model-agnostic meta-learning, or MAML, and its variant called almost no inner loop, or ANIL, together with online fine-tuning. As shown on the left, meta-learning stage has 2 components, the outer loop and the inner loop, through which the model is placed on a middle ground between channel distributions, or tasks, as termed in the original MAML paper, without specializing to either one. The goal of meta-learning is that model parameters are close enough to the optimal parameters of each channel and have a sensitive state, so it can quickly fine-tune to one of the channel distributions with few-shot learning. Also, as shown on the right, the difference between MAML and ANIL is that MAML requires full model fine-tuning, while ANIL requires fine-tuning of the last layer only. Despite benefits, the challenge with meta-learning is that the inner loop and the dataset sizes grow exponentially with the number of users, which limits its applicability in multi-user MIMO. To solve this issue, inspired by recent advancements in fine-tuning large language models, I introduced low-rank adaptation, or LoRA, for fine-tuning deep learning-based hybrid beamforming for the first time. LoRA paper that was published in 2021 suggested to freeze the pre-trained model and add low-rank matrices called adapters to each layer, as shown here. And during fine-tuning, we only trained the LoRA adapters, and since they are low rank, as low as rank 1 or 2, the number of trainable parameters is going to be very low, which makes fine-tuning very quick. These key advantages of LoRA offer a scalable and more efficient solution compared to the state-of-the-art, which is meta-learning. I applied LoRA fine-tuning to both system setups introduced earlier, System A and System B, to evaluate its effectiveness. System A, that is based on ResNet, serves as a simpler model representing a broader class of deep learning-based beamforming applications. Then I generalize it to System B, which is based on ADA-SE ResNet in the presence of hardware impairments. As shown on the left, in ResNet-based systems, LoRa adapters are added to the convolutional layers. On the right-hand side, for ADA-SE ResNet-based systems, LoRa adapters are also only applied to the convolutional layers and not to the attention module. This is because channel distribution shift is mainly experienced in the ResNet branch that processes the channel, And because of that, adapting the attention module wouldn't reduce the mismatch or the distribution shift. Also, the attention module is inherently low rank and would be overpowered by LoRa adapters if we add them together. Next, I'll compare the performance of LoRa and meta-learning. Here I'm showing the fine-tuning results for system A, simulated in the absence of phase noise. In the thesis, I reported all possible 12 transitions between channel types and how different fine-tuning approaches compare with each other, but I only show one sample transition here in the interest of time. In this simulation, the model is trained using CDL type A and fine-tuned and tested using CDL type C. Numbers 128 and 512 shown next to the markers are the number of fine-tuning samples. We can see that anneal is very parameter efficient, is far to the left. However, it does not show impressive improvement compared to the pre-trained model, but it's very light. Its full model fine-tuning version, or MAML, is far to the right, not very parameter efficient, and the improvement compared to the case we do fine-tuning without meta-learning isn't that impressive either. And that's mainly because the number of fine-tuning sample is very low, is 128 or 512. And MAML will require more than that for fine-tuning. So it's not very, very applicable to our scenario. In the middle, we see LoRa. So it is striking a good balance between parameter efficiency and performance, with LoRa rank 2 outperforming higher ranks. And that is an interesting observation because it essentially means that if we don't have many fine-tuning samples, actually using lower rank adapters in LoRa method is gonna perform better compared to the case that we use higher ranks. And as we increase number of fine-tuning samples, we see that this gap shrinks. So if we are comparing these ones attributed to 512 samples, we see a smaller gap, and potentially if increased number of fine-tuning samples, this slope is gonna flip, and higher rank are gonna outperform the lower ranks. However, in this application, we only have very few samples for fine-tuning, so LoRa rank 2 is the best choice. In this slide, I'm showing the simulation results for system B in the presence of phase noise, which is the main hardware impairment we are considering. For this simulation, I consider an urban area in Munich where 4 users randomly wander around the base station using the shown trajectory on the left. Multipath channel is simulated using NVIDIA's ray tracing tool for every user location. On the right-hand side, we see the complementary CDF of throughput, which at any position on the x-axis shows how frequently the throughput is at or above that level. So higher is better. We can see that LoRa rank 2 outperforms the rest of the methods with its average throughput almost twice the average throughput of the pre-trained model. I'll conclude my presentation by reviewing my contributions in MMTC and EMBB. In MMTC, my work improved the reliability and energy efficiency of the state-of-the-art Grant-Free NOMA. This work is published in IEEE IoT Journal in 2021. In EMBB, my research on beamforming predistortion improved the robustness of the state-of-the-art ResNet-based solutions against hardware impairments. We have patented this method last year, and it is under review to be published in IEEE Transactions on Wireless Communications after 2 rounds of reviews. In high mobility scenarios of EMBB, my research on efficient fine-tuning mechanism improved the robustness of the learned beamforming solutions against channel distribution shift. The results of this research is already published in IEEE Wireless Communication Letters, February this year. I also propose two research directions stemming from my thesis. For MMTC, I propose researching how predictive models can be used for dynamically adjusting the Grant-Free NOMA transmission and retransmission parameters for optimal performance. For EMBB, I propose to extend our hybrid beamforming system and fine-tuning technique to integrate them into the end-to-end optimization of the entire physical layer, which is a growing trend in wireless communication. Thank you so much for your attention.